All right, let's get started. We got a lot of things to cover today. So we have a lab tomorrow. So labs and a couple of other things we have to talk about. First, make my mouse easier to. From here, I'll just let you know. So all the notes I took from actually Dr. Kelston's website. For the lectures, if you go to the lecture itself, so you guys know that there's a lecture and lab web pages, right? So if you go to his, let me start a new page. This one, right? There are lectures and there are labs. So in the lectures, I already told you guys, if you right click and look at the source code, right click, view page source, and you scroll down, you can see the solutions to the questions being commented out. So you can refer to the solutions to find out the solutions to the questions. And I put most of them into a .c file with comments or things for both teaching and just the reference for both you and me. And so these are all the questions that are compiled into one file, but definitely not executable. It's not a C file. I just have so many different things in there, but just problem by problem. Okay, so I was looking at this before I come to the class, so I know what I want to cover, what I have to cover, and if you go to my website, you will be able to see them. I just posted them actually. If you don't want to spend too much time on the website because there are no clear step-by-step, because it's just so much information on the website, it could be a very good reference. But if you just want to directly get into the questions, you need to know to prepare for the exams. It's good to come to all these W1, W2, which is week 1, week 2 _ notes. So for the first week, because we didn't introduce C yet for the first week, so it's going to be a PDF file with all the questions and.
Have you listed exam dates? Because I was trying to find exam dates in order to schedule them.
Yeah, that's what I have to do this week. I think I have to submit a couple things. I'll figure it out.
Okay,
I'll let
so
you know.
Will be putting exam dates up soon?
Yes. There'll be 2 exams, right? Yeah, I'm gonna fill this up this week, most of them this week, and though also send the exam to the testing center, and there's just so many things to do. All right, just showing you that if you click week 2's notes, you can see the questions that I grabbed from his website and also solutions to it. All right. It's not executable, right? It's just examples and comments. And for week 3, I just posted. All right, so now let's go to week 2. I have something to talk about really quick, which is a race here. For the 1D array, sorry, to find out, it's on the top. Let's come to this one. Did I have that? Yes, I do. This one. All right. Okay, let's look at the first one. I'm not sure if I can uncomment everything by Control/. No, it doesn't work here. But let's take a look at the first one. So the thing you need to know for 1D arrays, I know it's commented out. I'm not running this. Don't have time to do it. There's so many things to cover for the lab tomorrow. Anyway, so look at this array. It's a 1D array. So you need to put the 1D array's name and just an empty bracket into the function prototype and declaration. So for example, in here, this one is not the function itself, right? We put a function on the top. It's a function prototype. So you will have this function below, down here, and the details of the function. However, on the top, you have to declare it. It's called a function prototype. And in the function prototype, you also have to put the arguments in there. So if you have one of the arrays as an argument, if it's a 1D array, you just put an empty, just a bracket over there, instead of having the numbers inside. However, when you call it in the function, for example, this function, I have to use this one as an argument to pass it into the function. So in that case, you don't have any numbers following that, just the name of the array. That's for 1D array, okay? For 2D array, you have both the row and line number, column numbers in the prototype, function prototype or declaration, okay? But however, when you are calling the function and parsing this array into that function, you just have the name of the function. It's just a convention. I tried it. If I can, leave this blank or put a number here, it just didn't work. There's no other things that you need to understand. You just have to follow the convention. That's how the C programming language is designed. You know what I mean? And both the two examples are posted on my website. So whenever you are getting confused about what you have to, how you have to use our arrays into your code, you can always refer to this example. So you can see where you have a numbers following, where it's just an empty bracket in there, right? It's nothing. That's one thing I want to bring up. Okay, other things, more importantly. So let's open up I think this is lec7. Let's do the in-lab first. MP. We have to look into all these MCC files, so that's why I have to open up the IDE. MCC. It's a configuration environment at the very beginning of the project. Starting from lab 3, you have to go through the MCC configurations at the very beginning of the lab, which is not hard to do. But the thing is, if you go to my website, I'm going to show you step by step. Which, for example, lab 3, if you go to Dr. Carlson's lab, there are no snapshots. That's why I posted my the pictures I did, or the snapshots I did when I went through everything. So here, super important, including lab 3 and all the following labs. If you see the MCC content type like wizard at the very beginning of the project, there will be a window pops up. In the future, you'll see, letting you setting up the timers, registers, and everything. Never click next. I think the TA already told you guys. Never click next, because if you click next, it will send you to it's called MCC Medley. I think that's a newer version of MCC, and a lot of things just didn't work. I tried. I think that was like lab 5 or something. I was trying to get a UART to work. It didn't. I don't know if it's just for that lab or for something else, for all the other labs as well, but it just didn't work. So you have to use the traditional one. You have to click this one, click here, right? There's a link, click here, and follow the step-by-step instructions over here on my website. You can also read through Dr. Carlson's website. They're just mainly text. You can read through that if you prefer that. Either way, go through every single step. Since I just did everything just a few weeks, I think 2 months ago, I think in the summer. So whatever the changes made to the newer version of the software probably will be reflected in my tutorial instead of in the older ones that he posted for some of the cases. And I did see little minor issues and bugs when I followed his website, all the steps, probably because the version he used was a little bit older. So sometimes if you had issues, by following his instructions, you can always refer back to mine, and hopefully that will solve your problem. Just to let you guys know, since I just did it 2 months ago, it should be a very similar version to whatever you have downloaded to your laptop. You see, if you look at these settings, it just mainly set up the crystal, because the microcontroller has a certain frequency running over the the core, which is 16 megahertz is the frequency that we use for all the labs. However, you can change it to something else. However, we are not changing it for all the labs. So at the very beginning, you set it up as 16 megahertz using that little nice GUI. So if you don't use that GUI, there are definitely other ways to do it. I'm going to show you this really quick, even though it's not really clear. No, it's not visible. Let's change it to the IDE. Let me see if I can find it. All right. So after you did all the setups or settings in MCC, I know you couldn't see it, but it's recorded. You know that area, right? So on the left-hand side, there's a menu, drop-down menus, and you'll see here. Can I zoom in? Probably not. Nope. There are files called mcc.c. If I double-click, so after you did all the settings in the MCC GUI, like I showed you, all the steps over here, it's gonna put the numbers to the registers as a configuration to turn on off certain functions. So this is what we are going to go through today, because probably most of you haven't done that yet, right, in the past. So for dealing with microcontrollers, 50% or even higher amount of time that you are dealing with the registers, because it's just like a user manual. You just purchase a new equipment in your house or in the lab. You have to read the menu, like which one you want to turn on, which one to turn off to serve your goal the best. Right? It's the same thing. The microcontroller is just a little tiny chip. There's no switches to ask you to turn it on and off. Different functions, right? So you have to use registers. So they provided so many different registers, and you can find on the data sheet. Okay, I'll show you one by one, I think, instead of page over here. Yeah, I'm going to show you one by one. So this one, okay. Do you remember what's the way to zoom in this page? Alt, not Control. It's Alt and the scroller wheel. So see the oscillation control. I didn't even bother getting into the details of the oscillation registers, since they're less important. You know, after you go through the MCC, definitely if you go to the website, go to the data sheet, you can find out the registers. For example, I'm searching for, you see OSC con, right? So by looking at this short name, you know it's oscillator control. So all the time you see a con, C-O-N, it's a control. So controlling the oscillator frequency, I could tell. And this hex number, why is the hex number? Oh no, so first, why is the hex number? Easier to manage. You don't want to just directly type every single bit for 16 bits. It's just two bits or 2 hex bits will cover 8 bits, binary bits, or 1 byte, right? And let's search for that. Just showing you. I have never searched for the oscillator control register, but now let's search for that and see what's in there. So I would just directly download the datasheet to the desktop. So whenever you need to search for anything, just go ahead and do it. Search. Okay. And next. So oscillator control, you got the explanation about the oscillator control register. There are 8 bits. Why all the registers are 8 bits? Yeah, it's just how they design the system. But usually the 8-bit 8-bit CPUs are using 8-bit registers. It seems like this is a 16-bit microcontroller, but still using bytes, 1 byte for the control units, which is okay. We don't have to worry about that because we don't need more bits. 8 bits will cover all the bits, right? If it's not providing enough space to host all the control bits, you just get another one. For example, it's the oscillator control register, and if you need more bits for more functions, you just got another register called like oscillation control 1, oscillation control 2. That's how that usually being named. Keep going. See here, that's usually what you want to look at. It shows all the details of the register. Okay? If it's the first time you guys working with microcontrollers and registers, highly recommend it. For the first few times you program it, just directly get into the page. Looks like this, with the title, right? The title, which is the name of the register, okay, and the full name of it. It's the oscillator control register, and showing you every single bit's functions. So for the first 2 bits, 0 to 1, it is something I don't even know. I never mess with it, which is okay because you set up everything in the GUI. Why do I have to bother waste of time? But first time it's good to take a look at it, right? So whenever you are wondering what are the lower 2 bits are doing over here, I mean, it doesn't mean I like this PDF editor, okay? It's just free. I mean, I have Adobe installed as well. Just anyway. Look at this lower 2 bits. It's bit 1 to bit 0. Shows you if you give a 0, 1 to it, it's doing what. If you do a 0, 0, if you write a 0, 0 to the lower 2 bits, it's doing something else, right? And now, if we look at this one, let's just look at it. For this register, it writes a 7, 0 into it. 7, 0 means 7, 0 means what? It's gonna be 1, 1, 1.
0, 0.
Sorry, 0. Right? This is 7.
And then 0 is
And all zeros, right? Okay. So which one controls the frequency? Let's take a look. Seems like here, right? So bit 6 to bit 4, which is exactly these ones. Oh, 0, 1, 2, 3, 4, right?
Yeah.
4, 5, 6 has to be what? 1, 1, 1 to make a what? 16 megahertz, right? So you don't have to manually set it up. Definitely you can. You can start up a file, mcc.c, whatever you want to name it, and have all the settings over here manually set up by yourself. However, if you follow the GUI, it will automatically generate the the settings for you, which is nice. Okay. But in the past, I think when I was in undergraduate, I also programmed the PIC for multiple times. I used to, because this GUI was not, or this IDE was not available. It was a very simple version of the microchip programming interface. So we have to copy and paste all the settings from project to project. So once you set up everything, you just keep copy and paste to the new project. But the first time you do it, it takes a lot of time. However, right now we are using MCC, so no worry about that. Don't have to worry about that. So the MCC.c file, I double click, you can see the .c file. The settings is already automatically generated. Okay? And for all of these ones, I don't want to get into every single one because we have more important register to talk about. But now let's go to, let's see. Okay. So remember this name. System initialize. And you can see the main.c file was also generated by, it was empty. So you have to add your code to it. But however, for the in-lab, it's different because all the code for the in-lab is already provided in here. So what we do is we just copy and paste into the main.c file, just overwrite whatever has been generated by the MCC procedure. And you can see the code provided in the main function already has this system initialize. System initialize. It's a sub-function being generated by the MCC file. If you double click, you can see system initialize. What this does, it does 3 other sub-functions. You have to deeper somewhere else, okay? Be prepared. So pin manager initialize. So pin manager initialize sounds like it's the pins setups, right? Sometimes you have an analog pin, it's multiplexed, has analog input, ADC, digital input output. If you are using them as digital pins, if they're multiplexed, you have to turn off the analog function and turn on the digital ones. Sorry, it's boring. It's getting boring. But so tomorrow you just have to deal with this in the lab. So pin manager, let's go to the pin manager.c file and take a look at it. Pin manager. I'll let you guys tell me, have you learned this before? No? So there are mainly three registers for the GPIOs. What this stands for? General purpose, right? General purpose IOs. All right, let's take one step back. This is getting deeper and deeper and getting, people are getting frustrated because it's just so new, right? You haven't played with microcontroller yet. Anyway, so why do we want to play with the GPIOs? Just take one step back. Don't think about the details of the lab and anything else.
Is it just because it's industry standard?
But I want to one step back, right? Just for using microcontrollers. So first, ask one more question. So what's the advantage of using microcontrollers? For example, like we control the peripherals, right? Like LCD, LED, motors.
They're small, cheap, and they have a lot of like customizability.
Yeah. The pins, right? So all the pins are available to you, and you can write or read from the pins. So basically, the embedded systems are outputting or inputting digital signals. So digital signals are nothing but just the pulses, right? Okay. And when you are displaying, you probably haven't done that yet, but hey, yeah, actually IPGA is digital logic. You probably have done that 7-second display stuff, right?
Yep.
If you use my controller to control it, I have four in one. Okay, 4 in 1. How do you display a different digits? For example, I want to display 7, just random number. Okay, 8, 7, 1, 8, 8. Right? But they share all the data pins, just the one set of data pins. How to display different numbers?
If you to target the pins directly,
Yeah.
by turning specific ones on and off.
Yeah, you scan it, right? You scan it. So what happens is you enable the first one, you throw an 8 over there through the shared data pins, the data lines, and then you turn it off and turn on the second one. And then you throw a different number, and then you turn on the third one, so on and so forth, right? You turn on each one one by one. And if you scan that really quickly, your eye cannot resolve it, so it shows a static 4 digits. But actually, if you have a super high-speed camera, they are blinking, okay? Since your eye cannot resolve it. And you can scan that really quickly. You enable, throw a number, turn it off, enable, throw a number, turn it off. Since you can do it super quickly, it looks like it's static, but actually it's not. All right? So why you want to use a microcontroller to do it? Since your microcontroller can run it super fast, can scan it super fast. Okay? So you can run it in a microsecond level or a millisecond level, so you can do that really quickly. And these are all controlled by the GPIO pins. You are throwing digital numbers to the pins, which are controlling the single LEDs on and off, and also the scanning pins as well. So that's why you want to use microcontrollers, because they can run super fast. So the one we are using is running at 16 megahertz. So what does that mean? It's oscillating, so every single period only takes 1/16 megaseconds. So in 1 second, it oscillates 16 mega times. It's running super fast, right? Okay. So the GPL pins, every single GPL pin of the microcontroller we are using has, for example, port A, B, C, D. You probably are not using B and C. We use B a lot, but C and D's sometimes. But port A and B, for example, or every single port, they have 3 control registers, mainly 3 control registers. Probably others as well, but the main ones that we are going to use, the first one is called tris. So it's tris A or B, something like that. So it's usually tris X. So if you are searching for tris A in the data sheet, sometimes it's not getting you to the correct page, like the one I just showed you. Because this is applied to all the A, B, C, D ports, so they use the X instead. So instead of searching for tris A, search for tris X. Sometimes it'll give you better results. Make sense? And then another register is called port X. So if it's port A, it's going to be port A, port B, port C. But in general, the general name is port X. Another name is lec7. And they are being used for certain purposes. And you have to set them up every single time when you use it. However, the GUI, the MCC GUI, will go through all the steps and did it for and do it for you. So tris is the direction register. It controls in or out. Let me show you one more thing. I know I've been in classes like this a lot in the past. I got lost a lot. That's why I didn't go to the classes when I was in undergraduate, which was wrong. But the teachers didn't teach actually, so it's okay. I learned a lot from outside of the class. Let's see what you're expecting. Twinkle, twinkle, little star. Not exactly, but. Huh? I know it was not accurate because I didn't insert that delay in between. Anyway, something was wrong. Don't blame me on that. So you need a pin to write to the speaker, and it's giving a command to the speaker by pressing a button. So what's happening is you press the button to start the music, and then one of the pins is writing that different frequencies to the speaker. So you need the pins, one pin taking the input, and another pin outputting to the speaker. 2 pins, actually 3 pins, because we have two different music pieces. So upper pin, bottom pin, the 2 buttons on the board. You press the top one, play one music, press the bottom one, another one. You know what's the greatest part of the U.S.? You guys are the students in the U.S. I think that's the greatest part of it, which is higher education. You probably will never find this type of education somewhere else. You guys are lucky. I'm not bragging about my teaching. I'm just saying what I learned from Dr. Carlston and my professors when I was in my PhD in graduate school is totally different from other countries. It's just so different. You see, he already provided everything on his website, and I did again on my website, just showing every single step. You guys are spoiled.
Yes. Yeah.
Hopefully you can take the time, spend time, and work on it. It doesn't like me when I was in my undergrad. I want to spend time on my work, but no instructions, nobody teach me. So it's good, you know. There are some other things I have to talk about, but let's don't skip too many things for now. So now you see the names. It's not unfamiliar to you anymore, okay? LAT, tris, and this is something else I want to talk about. But now let's come back to this one before we move forward. So tris defines the input and output. Keep in mind, usually 1, because 1 looks like I of input. So usually, not just for PIX, but also for other platforms, usually 1 stands for input. If you write a 1 to that bit in the register, it's turning on the input function. It's going to input instead of pin as an input instead of output. Okay? That makes sense, right? So I looks like a 1. If you put a 0 in there, it looks like an output. Right? There's something that I turn off. No. So 0 is the output. So when you are writing into the trace register, you just put a 1 or 0 into it in order to set up that pin to be 1 or 0. For port, it's taking input. It's a data input data. So you are not setting anything. You are not setting up anything into this register because this is the input buffer. You know what I mean? So if you connect signal to port A, and the data will be written into this port register. So when we are trying to take out the data from it, just directly put a port A and then assign it to something else, because the data is already saved into that register. It's an input buffer. Okay. For this one, it's storing the output. So it's an output buffer. When you want to output data to outside of the world of the microcontroller, you have to write the data into this register. You know what I mean? So for example, I want to turn on all the LEDs connect to the 8 pins of the microcontroller. What I want to do is I just send FF to this register. Then it's going to directly send all the ones to the pins. That's the output buffer. And that's the input buffer, okay? You are not writing to this manually, because when it's connected to the signal of the pins, the signal comes in, it's already saved into this register. You can directly assign this as the values in here to another variable in your code. So these are the 3 main registers. These will be on the exams, okay? So the 3 main registers, I'm going to show you in the code how to use them really quick. But before we move forward, let's see. 0, 0 to the output buffer. What is this doing? I'm just clearing all the values in it, just in case it stored something previously, okay? Because these are output registers, I'm going to write into these registers later in the code. So, but before we do anything, I just want to reset it. Just clean, nothing in it. What about this one? Trace A. Trace A, what does that mean?
Is it input or output?
Input or output, right? Input is what? 1 or 0? 1, because I of the input is very similar to 1. So FF, you can see, port, which port is set as input? A port, or port A, is the input port. So all the A ports are inputs. Okay? For trace B, what is DF? What is DF? 1 1 1 0, right? Wait.
No, that's B.
0 1.
Yep.
B.
Yes. Uh-huh.
Yeah. So which one is input, which one is output?
The only one that's output is the
This is output, right? So what is this pin? What is this port? It's R, because this is B. We are dealing with port B, right? So it's RB what?
6.
0, 1, 2, 3, 4. And this is the one we are going to use in the lab.
Oh.
Why? Why you want to output something to it? You want to run the speaker. So RB5 is connected to the speaker. RAs, A ports are all ones, are all inputs. So RAs are being used to do what? Connect to the button. So you press the button, you raise the value. and do something in the code. So you read it because you press it, and why it is able to read it because there are inputs. Where did you set it up as the inputs? Here. Do you care about other B ports? No. So if you don't care about them, I mean, doesn't matter if it's F or other numbers. I mean, for these ones, do you care about that? Do you care about them? Do you have to worry about them? No, I didn't even use them. There are floating pins on the board. I didn't even use them, and they're output pins. I didn't even have them in the code. So it's okay if you have like 0, 0, 0, 0. Does that matter? No, but it's just confusing whoever is taking on this task and reading your code. Why do you have to set up the lower nibble to inputs, but you didn't use it? So if you're not using them, just put a 1. To differentiate from the output, right? That's probably why. Okay, what about this? So this is the analog selection. We don't use the analog. It's an ADC. ADC. What is the ADC? ADC. Yeah, A to D, and not log to digital converter. It's an analog circuit, not pure digital. So you can see this microcontroller is called ISOCs. It's a system on the chip. It's not just purely a digital chip. It has analog components on it as well. So usually if you have analog circuits in there, you just basically cannot really easily use the 5 nanometer technologies because you cannot design analog system in that more than that short transistors. So usually these SoCs has all the analog parts on it are somewhere around like 65 or higher usually. So ADC is taking analog input and convert it to digital. Okay, we're not using it, but however, some of the pins, for example, the A ports, I'm not quite sure, but just give you example, the A ports could be multiplexed. Why you want to multiplex it? If you just look at the chip, it doesn't have many pins. You got power, you got ground, you have other things, but sometimes if you connect this one to one 7-segment display, and 4 pins for the switch, and got 7 pins for the data, you got power and ground, it takes up all the pins. You couldn't do anything else. And why do you display something? You want to sense the temperature and display to it. And the temperature sensor takes another 5 pins. You're running out of pins. So you can either use a decoder or something. But anyway, it's something else we can talk about. There's another shift register that you can shift all the bits to the data pins. It's called 595, which will save you a lot of pins. However, for other purposes, you just want to multiplex it because some of the pins are being used like A ports. They are used as general purpose, which is GPIO, general purpose IOs, to turn on and off, just toggle it, right? To turn on and off like certain LEDs or output a certain protocol. You can definitely do it. But sometimes it's also being used as ADCs. If you don't have this multiplexed, you also want the customer to use, the user to do ADCs, ADC converters. So you have to generate more pins, which means you need a big chip, has so many pins on it, will increase the cost of the chip. So we have a tiny chip, has only like 28 or something pins, so a lot of them has to be multiplexed. So if the pins are getting multiplexed, you have to set up the analog selection pin because you want to tell the microcontroller this is not used as ADC port. It's a digital general purpose I/O. It's a GPIO. So for that case, for example, A port is 2-3, and hopefully this is visible. 2-3. This was printed out from the datasheet. Okay, you can always go back to the datasheet to find it, but I don't have time to search in there. This looks better, I think, compared to the previous ones. Right, it's clear, right? It's visible, at least. Okay, so search for that name of the register and take a look at it. Find out the data sheet, search for that. This is table you wanna refer to, right? So that the number was 23, right? We write to the register as 23. That 23, 23, okay. What does that mean? 23, 23. So 3 here is actually 0, 0, 1, 1, right? And 2, which is giving you a 1 here. But we are not dealing with these ports. So we are only working with R2 and R3, A2, A3 ports. So A2, A3, if you give a 0, what's going to happen? So which is 0, 1, 2, 3, right? So it's bit 0, 1, 2, 3. So first 4 bits over here. So 0 will enable the digital input buffer, right? So because A2, A3, these 2 pins are being used for the push buttons. Getting bored?
What's the digital input buffer? Is that just that tells it?
That's the port A. That's the port A. The port A is the buffer. So the buffer means it temporarily stores a value getting into the microcontroller.
Okay.
It's just a series of D flip-flops storing them and waiting to be latched.
Okay.
It's just a storage unit, like a memory bank or 8 bits of D flip-flops. So what I'm trying to show you is let's get to the lab. Lab 3. Oh no, the schematic. Tell me, what are the 2 ports for the button? Wait, no, these. What are these? R19, R20. What are they? That's a resistor's name. What about the 2 inputs connected to oh yeah, another thing for PCB, since you guys are not in the PCB class, still a surprise because no overlap, just 2 students are in the PCB class. Anyway, so if you look at the RA2 and RA3, they were not connected to anywhere. It's confusing you guys probably if you haven't designed anything in schematic. But if you name it as RA2, you see there's another RA2 here on the chip. It's actually electrically shorted to it. We just don't want to route it everywhere. It's confusing people. Got all the wires. Doesn't look good. So we just name it as RA2 when you are doing the schematic in Eagle PCB. You right click and rename it. It's going to ask you, hey, are you sure you want to short this one to somewhere else? Just click yes. Then it's going to electrically connect the 2 pins together without a physical wire. You know what I mean? If you convert this schematic to a PCB, you'll see the trace. The trace, it's going to be a physical trace connecting these 2 pins. But schematic doesn't matter. It's just a picture, right? It's the picture showing all the circuits. It's not a physical layout. Just a schematic. So showing you this is RH connect to RA2 and this is connect to RA3. That's enough. It already shows you everything. So if you press it, it's shorting this pin to ground. So you are reading a 0. Okay? So I'm just telling you how to find out the resource from the data sheet, but there are just so many things that I have to spend Friday probably to talk about it. But in the lab tomorrow, you know what to do. Just to go get into these files, you can see how they were set up. For the timer, right? So timer, I saw timer initialize, and the timer is writing a number here. Timer right, TMR is a timer 1, right in the timer, and you put a number here, and the timer is gonna, this function will take this argument into here, and shift it to because this timer register, the counts, has 2 bytes. Literally has no time to go through everything. I hope I have 3 hours for the lecture. Which you don't. You'll hate it. 1 hour is enough. So timer counts. This register has two bytes. So it's basically 1 byte, another byte, and you combine them together. Move this one here, and you get a 16-bit timer counts. Since we skipped Monday, it was Labor Day, that's why we are rushing. So you'll store one byte here, another byte here, but they have to be combined. You don't manually combine them, but the core actually reads them as upper because high, as low, as a higher byte and lower byte. So what does that mean? This is a bit register. Whatever number stored in here is actually has to be shifted to the left by 8 bits. Okay? So you are putting a 16-bit number into the function. It's a 16-bit number. It's a uint underscore 16 underscore t. It's a 16-bit number. So that number comes in. You have to shift that number to the right by 8 bits. What's happening is, for example, the 16-bit number is coming, right? You shift it by 8 bits. This will be shifted out. Only this one will exist at a lower byte. Okay? And you give this one to this register. Okay? And for the second one, this command from you are telling the timer from you, it's a 16-bit number, and this number comes in. For the lower byte, you don't do anything to it. Let's see if that makes sense. The data comes in, it's a 16-bit data, right? For the higher byte, you shift it to the right by 8 bits. This is out. So this one will be the higher byte. Makes sense. Put it here. And now I get the 16-bit, still the same number. I directly assign this one to this byte. What's going to happen? You assign a 16-bit number to an 8-bit number. What? What's going to happen? Only the lower byte will be saved because this guy cannot accommodate all the 16 bits. So what's happening is you are able to do the shift for the first step to get a higher byte out and put it in here. And the second time you directly give this 16-bit number to this register. So only this one will be saved, will be stored in this variable. But this ones will not because this one is only 1 byte. But this is longer than that. You know what I mean? Only the shorter byte will be stored in here. Another one is super important. I have to, 1 more minute. Let me see. Okay, let me do this really quick. I'll tell the TAs tonight, so make sure they will teach it tomorrow, okay? So for the bytes, it's counting at 16 mega times per second, all right? So for, no, don't have enough time. We'll do it tomorrow, the lab, all right? See you tomorrow.